surface subgroups of right-angled arcing groups. So basically, as I said in the abstract, I'm going to survey some of the new notions and basic concepts in geometric group theory, particularly concerning cubical complexes. So that's why I'm emphasized this talk will be self-contained and expository. So basically, the motivation comes from three-manifold theory, although we'll not really go into the details of it. So let's summarize elementary definitions before we move on. First of all, hyperbolic three-manifold is, well, by definition, is a manifold with constant Riemannian metric and the constant sectional curvature, which is -1. But more concretely, you can consider hyperbolic three-manifold as quotient of hyperbolic three-space by torsion-free discrete subgroup. So it is the definition of hyperbolic three-manifold. Actually, one can define hyperbolic n-manifold in this way. Consider hyperbolic n-space. So that is complete Riemannian simply connected metric space with constant sectional curvature -1. You cut it, quotient it by discrete torsion-free subgroup. One gets hyperbolic n-manifold. In the case when the dimension is 2, this definition is still true, but it has more concrete and easy definition. That is, a surface with or without boundary is called hyperbolic if Euler characteristic is negative. So in the case when the surface is orientable, we just call a surface of genus at least 2 as hyperbolic. So that is equivalent to actually the definition number 1 in the case of 2 dimension. And a hyperbolic is just a piece of terminology. A hyperbolic surface group means the pi1 of closed hyperbolic surface. Just consider this as convention because, well, you may well talk about pi1 of bounded hyperbolic surface, which is free. But we'll just restrict our attention to pi1 of closed hyperbolic surface, and that will be called hyperbolic surface group. That's just our convention. And another piece of terminology, or just kind of phrase, we say that a manifold is virtually something if some finite cover of it is something. So it is just kind of way of abbreviate long phrases. And a group is, so in the same way, a group is virtually something if some finite index subgroup of it is something. So there is correspondence between those two. Say this group is pi1 of M. Then a group is virtually P, and say a manifold corresponding to it is virtually P. Then a finite cover, the pi1 of finite cover of M, will be finite index subgroup of it. So there's this virtually means either you take a finite cover of a topological space or you take a finite index subgroup of it. So that's another phrase. And a three-manifold fibers, if, so it is again conventional term, if M is actually surface bundle over S1. So it is very concrete description of a three-manifold. That means you take a surface, say, S, and actually you take 2 copies, surface S and surface S, and consider a mapping torus. That means you consider a direct product, surface cross I, and you identify 2 boundary components by some homeomorphism, say some phi. So it is very concrete description of three-manifold. And many manifolds can be described in this way. You take a surface and consider mapping torus with respect to some homeomorphism of a surface, automorphism of a surface. And well, again, a topological space is aspherical if it has contractible universal cover. That means it's pi2, pi3, all the higher homotopy groups are trivial. And that basic definition comes in for the Haken manifold. An aspherical three-manifold is called Haken if it has a, in some sense, nicely embedded surface. More concretely, if there exists an embedding of a surface into the three-manifold such that it induces injection on the pi1s. So you can consider Haken manifold as a three-manifold with kind of scissors, a scissor or a cut point, so that if you cut along the surface, you get a simpler piece. So nicely embedded surface inside three-manifold is the definition of being Haken. So for a Haken manifold, many things are known. Actually, Haken manifolds are determined by its pi1. And Thurston's work was that if a three-manifold is Haken, then you can give a geometric structure to three-manifold, one of his 8 geometries. So it is a question of central importance that which manifolds are Haken, which three-manifolds are Haken. So virtual Haken conjecture asserts that every basically closed orientably reducible three-manifolds are virtually Haken, but the only remaining case right now is closed hyperbolic case. So virtual Haken conjecture asserts that every closed hyperbolic three-manifold is virtually Haken. Again, recall that this means that given any closed hyperbolic three-manifold, there exists some finite cover which has nicely embedded surface. Surface that is pion injectively embedded. And a stronger conjecture is actually virtually fibering conjecture. If we know this, then we will have very concrete description of any closed hyperbolic three-manifold, which is kind of, mystery word these days. So any closed hyperbolic three-manifold virtually fibers, that is a conjecture. That means that if a manifold, three-manifold is closed and hyperbolic, then it has some finite cover, which has this structure. So it is very bold and concrete conjecture. Actually, this virtual fibering conjecture is still open for bounded three-manifold too, but we'll just restrict our attention to the closed case also. So there is a well-known program to prove the virtual Haken conjecture. Actually, it is a two-step program. The first step, we prove that pi1 of the three-manifold contains a hyperbolic surface group. That means this pion M contains the pion of closed hyperbolic surface. So that is a step 1. And step 2 is we prove that the pion of three-manifold is LERF, another piece of language. So we say that a group is LERF. That is kind of acronym for locally extended residually finite, but well, nobody cares about the origin anymore. So that means any finitely generated subgroup of the whole group is actually intersection of any finite index subgroups containing it. So it seems a bit unnatural at first, but you'll see that this is really something like the definition of closed set in the point set topology. In the point set topology, a set is closed if and only if it is intersection of all the closed sets containing it. So in this case, well, actually there is a precise formulation of that. In this case, we define topology for the subgroups of given group, and H is closed if and only if it satisfies that. So again, H is, well, we say that pion M is LERF if this is true for any finite general subgroup. So any finite general subgroup, H is actually no smaller than intersection of all the finite index subgroups containing it. So in some sense, this means that pion of M has lots of finite index subgroups. There is an abundant set of finite index subgroups of pion M, such that it is sufficiently abundant such that any finite general subgroup is precisely intersection of any finite index subgroups containing it. So the purpose of those two-step program is as follows. So by step 1, suppose pi1 M contains a hyperbolic surface group. So there is a map from a surface group into fundamental group of the hyperbolic three-manifold. Then basic geometry, basic topology tells us that one can realize this embedding of pi1s as immersion of surface. One can locally inject map S into the three-manifold. That is step 1. And step 2, well, Peter Scott about 30 years ago proved that if the fundamental group of a three-manifold is LERF and there is a immersion of surface, then that immersion leads to a embedding in some finite cover M prime. So step 1 finds immersion. Step 2 manipulates the immersion to an embedding in some finite cover. So if these two steps are true, then virtual Haken conjecture will be true, although that doesn't say anything about virtual fibering conjecture. So again, the meaning of virtual Haken conjecture is if you know that a certain manifold is Haken, then you have a very nice tool that is surface they can cut the surface, cut the manifold along the surface, and you have a simpler structure. And actually, step 1 turns out to be true by a very recent result by Khan Markovich. It was proved in August last year. So step 1 turned out to be true. So any closed hyperbolic three-manifold group turn out to be containing a surface group, hyperbolic surface group. So we know that there is an immersed surface, although we do not yet know whether there exists an embedding of a surface. And Gromov, so today we'll not really talk about the proof of step 2. Rather, so step 2 is still wide open. And we'll talk about some meaning of step 2, but we'll not really talk about the possible approach to step 2. Rather, we'll talk about a generalization of step 1. So closed hyperbolic three-manifold groups turn out to contain hyperbolic surface groups. So is it really of geometric reason, or is there any other algebraic or more elementary reason? And motivated by this, Gromov made this even bolder conjecture. He asserted that, he questioned that any generic finitely presented group contains a hyperbolic surface group. So this means that given any finite presentation of a group, infinite, of course. So given any infinite finitely presented group, with probability 1, it will contain a hyperbolic surface group. So it is really bold and very bold conjecture with very little bit of evidence. Well, basically it is very recently proved for closed hyperbolic three-manifold groups. But what about generic groups? Why would it be true? So today I'll talk about some presentations called right-angled arcing groups and ask the question, when does it contain a hyperbolic surface group? And more geometric formulation of what I've just said is we're going to talk about so-called cubical complex today. So it is not a three-manifold, although it is motivated by three-manifold. Cubical complex is a cell complex, CW complex, obtained by just taking lots of cubes. Cube includes, say, vertices or edges or two-dimensional squares or three-dimensional cubes. Consider lots of those pieces. And you make a cell complex by side pairings. That means you can consider, say, three-dimensional cube, and you attach a square in this way, and you allow self-identification of boundaries like circle, or it is well known that you can identify two-dimensional square, the opposite sides of two-dimensional square together, torus, something like that. Any CW complex you can obtain by side pairings of cubes, like three-dimensional, two-dimensional, one-dimensional, and so forth. So for example, circles or figure 8, wedge of two circles, or square or torus, they are all cubical complexes. So that is the geometric object that I'd like to talk about today. And we define a link to be intersection of sphere. SV means small, sufficiently small sphere around it of various dimensions with the cubical complex itself. So this link is kind of way of looking at the local picture of a point, reducing one dimension. So for example, if one has this one skeleton of unit cube consisting of, say, 12 edges, then the link of the blue vertex will be just consisting of 3 red vertices. You take a small sphere around it. The intersection consists of 3 red vertices. So if you have two-dimensional unit cube, that means, what is it? This is actually topologically a sphere, two-dimensional skeleton of three-dimensional cube. And you take a small intersection with a sphere, then one gets a circle, topologically a circle, and combinatorially a triangle. And if one considers three-dimensional filled-in cube, and you cut it by a small sphere around the vertex, then you get a filled-in triangle. So this is the definition of link, and the importance of it was motivated by this Gromov's definition. So Gromov's no-empty triangle condition for a cubical complex says the following. A cubical complex is called non-positively curved if any complete graph in the link spans a simplex That means if, say, cubical complex X is given, and look at all the links. Say, suppose the link of the complex at some vertex looks like, well, it's one skeleton looks like something like this. Something like this. Then actually the link must contain all the simplices spanned by those one skeletons. So in some sense, the link is determined by its one skeleton. Whenever one sees a complete graph, that must be filled in. Whenever one sees a complete graph, that must be filled in by a simplex. So, right, he called it as non-positive curve because this non-positive curve cubical complex has very similar structure to Riemannian manifold with non-positive curvature, sectional curvature. So, and these first two slides are kind of advertisement for non-positive curved cubical complex and right-angled arcing groups. So we'll mostly talk about non-positive curved cubical complexes and right-angled arcing groups rather than three manifolds, but I'll mention a little bit of motivation to study them. So we say that a topological space is cubulated if it is homotopically non-positive curved cubical complex. Again, cubical complex consists of lots of cubes and side pairings, and we call it non-positive curve if it satisfies this link condition. All the complete graphs are filled in. And topological space is cubulated if it is homotopically non-positive curved cubical complex. Then Eigel's recent theorem proves that given closed hyperbolic three-manifold, if the step 2 is true, so let me recall LRF. So group G is LRF if and only if any finite generated subgroup H is intersection of all the finite index subgroups of the whole thing. Containing H. So this is the definition of LRF. And if pi1 is LRF, then M is virtually cubulated. Some finite cover is cubulated. So it basically proves that, again, by the recent proof of geometrization theorem by Perelman, every three-manifold has a geometric structure. It can be cut into small pieces having various geometric structures. And the most mysterious one, the most unknown one, is hyperbolic pieces. But it shows that those hyperbolic pieces are basically conjecturally cubulated. So I said it conjecturally because the step 2 is proving that pi1 of closed hyperbolic three-manifolds are LRF. That is still a conjecture. But if that conjecture is true, then any closed hyperbolic three-manifold will be virtually, some finite cover of it will be cubulated. We'll have a cubical structure with non-positive curvature. So it proves that basically non-positive curved cubical complexes are everywhere in three-manifold theory. And it is conjectural for any closed hyperbolic three-manifold. And there is something more than one can say about closed hyperbolic three-manifold with LRF fundamental group. If, say, even it doesn't have to be a manifold, if a space is cubulated with LRF pi1, then pi1 virtually embeds into some nicely defined group called right-angled arcing group, which I'm going to define in the next slide. So that means that, well, just like in the previous theorem, in the conclusion of previous case theorem, if X is cubulated with LRF pi1, then that pi1 virtually embeds into some very nice group called right-angled arcing group. And by studying subgroup structure of these right-angled arcing groups, one will have more understanding of such pi1 of X. And how nice is it? How nice? Well, I didn't even define right-angled arcing groups, so it would be really nonsense to talk about right-angled arcing groups. But let me say one more theorem concerning right-angled arcing groups. Now, given closed hyperbolic three-manifold, if pi1 virtually embeds into that mysterious object, right-angled arcing group, then actually M virtually fibers. It has very concrete structure that I've just erased. So conjecturally, any closed hyperbolic three-manifold groups are LRF. So it is cubulated. And if cubulated, then still conjecturally pi1 is LRF. Then pi 1 is embeds into some right angled arcing group, which I'm going to define in the next slide. And the right angled arcing groups are so nice. Very tight control on subgroup structure. So that if closed hyperbolic three-manifold group virtually embeds into some right angled arcing group, then M virtually fibers. Therefore, combining these three, basically this pi on M lerf is the only remaining conjecture for the whole series of conjectures concerning closed hyperbolic three-manifold groups, or closed hyperbolic three-manifold. If closed hyperbolic three-manifold group is lerf, then in the end, M virtually fibers. We have very concrete description. Very concrete description. Any closed hyperbolic three-manifold is fiber bundle, surface bundle over S1. So the only remaining factor to consider, or the only remaining variable for closed hyperbolic three-manifold will be that surface automorphism, identifying two boundary components of surface bundle. So again, you can consider these three slides as an advertisement of what we are going to talk about in the remaining of the talk. For the remainder of the talk, we'll talk about cubical complexes and right-angled arcing groups. Right-angled arcing groups is really a very simple concept defined by a finite graph. So just take a finite graph without any further structure. So it's unoriented, no multi-edges, no loops. So it is just pure simplicial combinatorial graph. Just take any finite graph. Then one can consider this as the most natural notion of group defined by a graph. So let us denote the vertex set and the edge set by V gamma and E gamma. Then the most natural group that one can define using the graph is as follows. The right-angled arcing group, depending on gamma, is a group presentation where vertices are generators, and for each edge, there's a commuting relator between those two vertices. So it is really a very simple concept. So if you have a vertex, right-angled arcing group of vertex is just Z. One generator, no relator. You have, say, two generators and one edge joining them, you get Z cross Z. And so forth. If you have triangle, three generators, and these two commute, these two commute, these two commute, so you get Z3. Or we can consider any other graph, something like this. Then the right-angled arcing group on this graph will be generated by 1, 2, 3, 4, 5 generators. They are all of infinite order, and these two commute. Right? So you add some commuting relators between the generators. So it will be some arbitrary group. And a more familiar concept to many one will be right-angled Coxer group. So right-angled Coxer group is a special case of a Coxer group. In this case, we have the same generators and same relators with additional one, declaring that each generator is actually an involution. So that is a special case of Coxer group, and one can see the motivation of calling those as right-angled, because, well, in the general case, if you have a Coxer group on, say, well, traditional notation was W. Coxer group of, say, two generators with the label M, with, say, vertex 1 and vertex 2. Then this group was V1 squared, V2 squared, and V1, V2 to the M, generated by V1 and V2. And relators are, each generator is an involution, and V1 to the M power is trivial. So this is traditional Coxer group. And this, our case, appears if you take M as 2. And pi over M was the dihedral angle between the reflecting hyperplanes in the definition of Coxer group. So right-angled Coxer group, we call them as right-angled because that is motivated, that is a special case when the dihedral angles are all pi over 2. Right, so right-angled arcing groups are relatively recently defined. That means defined about 3 decades ago or so. So right-angled arcing groups are defined by graphs. Vertices are generators. For each edge, there is a commuting relator between the vertices. So it is defined, it is called RAG by obvious reason, a right-angled arcing group. Or more, some time ago it was called semi-free group. It's like a free group generated by some vertices. But it is called semi-free because we have some commuting relators. Looking at from the other extreme, one can call this as partially commutative group. That means it is like a commutative group generated by vertices, and there are commuting relators, but it is partially commutative because there are only partially commuting relators between the vertices. And it is called graph group because it is defined by a graph. So example, so already given, right? So one thing to notice if one can prove that right-angled arcing group on a tree is actually a three-manifold group. It is fundamental group of certain link complement. So one may see three-manifold groups or any other groups in right-angled arcing groups. Yes? No, I don't have to assume that. But it is interesting to note that if, say, graph is disjoint union of two, then the group is generated by vertices, and there are no relations whatsoever between vertices here and vertices there. So it is actually a free product. So you have several connected components. Then we have several free decompositions, free factors in the corresponding group. So the following was actually, one can just go on. There is a very long list of surprising properties for right-angled arcing groups. But one fundamental thing to note is the group determines the graph. So obviously the graph determines the group, but the other way around also. Given a group, there is only one possible graph that yields the isomorphic type of the group. In other words, if two right-angled arcing groups are isomorphic, then the corresponding graphs must be graph theoretically isomorphic. So it's like studying right-angled arcing groups is, in principle, same as studying graph theory, because there's a one-to-one correspondence between those groups and the graphs. So it was first proved for more general notion graph algebra for Kim, Markov-Limanov, Negros-Rausch in 1980, and it was proved for these groups by Carl Drums in 1987. And right-angled arcing groups are linear, and one fundamental fact is one has smaller graph than larger one. So by full subgraph, I mean a subgraph spanned by the vertices. The maximal subgraph containing the given by the vertex set. So, and if gamma 1 is full subgraph, or some authors prefer to use the term induced subgraph of gamma 2, then right-angled arcing groups embeds in gamma 2. And as well, I just stated that already. Ego last year proved that if hyperbolic three-manifold groups embed into some right-angled arcing group, then the right-angled arcing groups, whatever the graph is, regardless of the shape of the graph, right-angled arcing groups have a very tight control on their subgroups, so that M virtually fibers. And this is really the end point, the goal of three-manifold theory. Prove that a hyperbolic three-manifold virtually fibers. Then probably we cannot have any further structure, we cannot study any further structure on that because it is just as concrete as we can get. So, and now the natural conjecture is, so is that always true? Given any hyperbolic three-manifold group, can you embed it into some right-angled arcing group? Well, that is still a conjecture. And if that is true, that will be really remarkable progress. And right-angled arcing group provides large amounts of examples or counterexamples in graph theory, three-manifold theory, computer science, even application to robotics. Well, the robotics is basically, in robotics, you are wondering configuration spaces of various robots in a path or graph or space. And the configuration space, the pi1 of configuration space, has certain relation with right-angled arcing groups. So motivating question for today is, when does right-angled group contain hyperbolic surface groups? So I'd like to apply Gromov question to right-angled groups. So when does it contain? So it's interesting question in its own right, but considering the recent development relating hyperbolic three-manifold groups to right-angled groups, one can consider this as a extended three-manifold theory question. So the first tool that I'd like to describe concerning right-angled groups is a certain geometric structure, geometric object, whose pi1 is the right-angled group. So given a right-angled group, I want to define some playground. So it is called Salvetti complex. So given a graph, say gamma is a graph, finite simplicial combinatorial graph, then one can define a cubical structure as follows. Cubical complex. The vertex set consists of just one vertex. No other vertices. One skeleton is just wedge of circles, bouquet of circles corresponding to the vertex set, corresponding to the vertices. And for higher cells, we attach a k-dimensional torus whenever we see complete subgraph of the graph, where small k is the number of vertices. So let me give you a more concrete example. So it will be more clear if you look at the example. Say gamma is only one vertex, then right-angled group is Z, infinite cyclic group. And the space is S1 because, well, there's only one vertex and only one circle corresponding to the defining graph, and there are no other cells. If there are Kn or just K2, for example, gamma is the edge. Say, let us denote the vertices A and B. Then right-angled group is Z2. Right-angled group is Z2. And moreover, the X gamma is torus because one has bouquet of two circles as one skeleton, and one attaches two skeletons, S1 to the 2, corresponding to this complete graph on two vertices. So we attach a torus, and A and B can be seen there. A and B can be seen there. So it is really actually after some consideration, one sees that this is some obvious thing to do to find certain geometric object such that the pi1 is given right-angled group. Say right-angled group is Z2. We already know that pi1 of torus is Z2. Or say right-angled group is Z3, then pi1 of three-dimensional torus is Z3. So we make a cubical complex so that pi1 is the given right-angled group. And if, say, gamma is discrete, then there are no higher cells, higher dimensional cells. Right-angled group is free, and the cubical complex is just a wedge of circles. So this process, defining process, stops at step 2. Let me give you a little bit less trivial example. So first of all, this right-angled group, one can check that it's non-positive curved. So again, recall that our cubical complex is non-positive curved if it satisfies certain combinatorial structure on the link, and pi1 is right-angled group. If, say, the graph is this cycle on length 6, say C6, let us denote the vertex set, vertices as A, B, C, D, E, F. So gamma is the cycle on length 6. Then what is the Salvetti complex corresponding to that? Well, for step 2, one consider bouquet of these 6 circles. Let us just label them by A, B, C, D, E, F and orient them. And for step 3, we attach a, say, two-dimensional torus for each edge, complete graph on two vertices. So corresponding to the edge AB, we attach a torus there, and corresponding to the edge BC, attach a torus. There are 6 tori attached to that. And that attaching is as follows. Say, identify one circle to the meridian and the other circle as longitude. And we do the same thing. So it's like the Salvetti complex consists of 6 tori glued in a cyclic fashion. So this is the Salvetti complex. So one can define, for any given graph, one can define right-angled group, and one can define this Salvetti complex. This is some natural notion, and the pi1 of Salvetti complex is the right-angled group. It is non-positive curve cubical complex. And step 2, well, the second tool that I'd like to employ is called cat-zero geometry. So cat-zero geometry is a generalization of notion of non-positive curved Riemannian manifold. If a Riemannian manifold has non-positive sectional curvature, then it has various properties, various consequences. That is the result by Alexandrov and Topogonov. And that concept, well, those results actually it turns out that those results, those corollaries, can be also obtained by putting some minimal assumption without any differentiable structure whatsoever. So it is really elementary concept. Given a metric space, assume that it is geodesic metric space. That means any 2 points can be joined by a length minimizing curve called the geodesic. So given metric geodesic space, we call it as cat-zero if and only if just take any geodesic triangle consisting of geodesics, say delta, and consider a comparison triangle, delta prime, of the same side lengths in the Euclidean space. If delta is no fatter than delta prime, we say that X is cat-zero. So by no fatter, we mean the following picture. So take just any geodesic triangle in X and consider another geodesic triangle in the Euclidean space. Euclidean actually plane, just simple R2. And assume that the edges of the same colors are of the same lengths. So you have pink edges, same lengths, so they look the same. Blue edges or purple edges, they are having same side lengths. Then no fatter condition means that take any point and corresponding point in the comparison triangle. So green edges are of the same lengths, red edges are of the same lengths. And join them from the other opposite vertex and measure the distance from P to that vertex. The no fatter condition means that D is at most D prime. So it is really elementary definition. No differentiable structures whatsoever. But it turns out that it is very robust condition, implying lots of facts. And the fact that I'd like to use about cat-zero geometry is one can use cat-zero geometry to achieve pi-1 injectivity between spaces. So that, terminology is, if a space is covered by cat-zero space, then we say that X is locally cat-zero, just definition. And the fact that I'd like to use concerning this cat-zero geometry is the following. Given local isometry, so local isometry means just isometry locally. Right? So given a pair of points, there is a small neighborhood such that in the neighborhood F is isometry. So if F is locally on isometry and the target is locally cat-zero, then it induces injective map on the pi-1s. So the proof is not so hard. So given locally cat-zero space and say any geodesic, well, one will have to assume that X and Y are both geodesic metric spaces, complete geodesic metric spaces. And given any homotopy class of a non-trivial homotopy class of a curve here, we want to show that the image is still null homotopy. That is obtained by choosing that curve as local geodesic, and local geodesics are mapping onto local geodesics by local isometry, and show that local geodesic will never be trivial in the target using cat-zero geometry. So that is a fact that I'd like to use. And another piece of knowledge proved by Gromov is that the non-positive curvature condition, which was very combinatorial. Given cubical complex, look at the links. Links are all simplicial complexes. And combinatorially, we define what the non-positively curved cubical complexes are. That was very combinatorial definition, but it turns out that it satisfies this global geometric condition, locally cat-zero. So that is the finding of Gromov. Given cubical complex, if it is locally non-positively curved, it satisfies certain that simplicial and combinatorial condition, then it satisfies local cat-zero condition. It has this global geodesic comparison geometry property. And Salvetti complex is non-positive curved, therefore it is locally cat-zero, so we can apply cat-zero geometry to find surface subgroups of right-angled arcing groups. So, and another nice thing to know is that local isometry, so in this fact, Well, everything seems like combinatorial now. Local Katsura property is combinatorial if they are cubical complexes. And by a theorem of Charry, well, it is a folklore theorem actually, is that local isometry, locally an isometry can be formulated combinatorially also. So that is saying that, well, so I'm not really going to the details of the technicality, but briefly, given a cubical map, so we have two cubical complexes and cubical map, and well, actually we'll have to assume that both are, say, locally Katsura. And then such a cubical map is local isometry if and only if, first of all, it is locally injective. That is obviously necessary. So locally injective means that the induced link map is an injection. So given two cubical complexes, one can consider links, local structures, local shapes. And the map F will induce simplicial map between the links. And the first condition is that the link map is injective. And moreover, the image of this link map is full subcomplex. The sub-simplicial complex determined by its vertex. So that means, say, given two cubical complexes, so say X is mapped onto Y by F. And say Y looks something like this. So say this is link of Y. So some local picture around it. And say X link of F maps image of link of F is the yellow graph, say this. Then the second condition means that the image is full subcomplex or subcomplex determined by its vertex set. So the image must contain the two cell also. So it is the maximal subcomplex of the target determined by its vertex set. So if these two conditions, these two technical conditions are said, technical but purely combinatorial conditions are satisfied, then F is local isometry and the other way around. So I'll just probably, for the remaining time, describe just one example of writing non-trivial case where writing Darting groups contain certain hyperbolic surface groups. And then I'll just describe some results, and that will be it. So consider surface of genus 2. So it's just pure surface without any structure. Now consider cycle of length 6, labeled by A, B, C, D, E, F. Consider its Salvetti complex. So it is one skeleton is a bouquet of circles, and tori are glued in a cyclic fashion. So I drew only one torus, but there are actually 6 tori. Now we define a map from that surface group into that writing darting group by the following structure on the surface. Consider this chain of 6 circles on the surface. 1, 2, 3, 4, 5, 6. There are 6 circles. And we're going to transversely orient them and label them by A, B, C, D, E, F. So we just consider this structure. So actually, right. So we consider chain of 6 circles, transversely orient them, and label them by the vertices A, B, C, D, E, F. So we consider this structure on the surface. So say choose a intersection point X and look at the local picture. The local picture at X will be, it is crossing with, say, F curve and A curve, transversely oriented from left to right for F and from up to down for A curve. This is the local picture. Now what we do is just combinatorial consider its dual picture. Consider the dual structure on the surface with respect to these green curves. So that means for each vertex, we're going to attach a two-dimensional square, two-dimensional cell like that. And for each edge, we're going to attach crossing blue edge. And for each region bounded by green curve, we're going to put a vertex. So for example, say consider the region in up and front of the surface, and we put a blue vertex there. blue vertex there. And then the transverse orientations of green curves and labels on the green curves carry over to the edges of the squares now we have defined. So instead of a chain of 6 circles, now we have a surface consisting of squares. In other words, square complex. So actually this was the motivation for various people to think about cubical structures. These cubical structures are just not a random structure one can consider for CW complexes. Rather, it is a very natural notion to consider to study manifolds, given certain transversely oriented things, objects. If you consider dual structures, then necessarily you will see these square complexes or cube complexes. So S is now a has cubical structure, consists of these squares. And actually there's a map. Now we have defined actually a map from surface onto the Salvetti complex. We just send these F edges to F curves and A edges to A curves. We just map this square spanned by A and F to the torus spanned by A circle and F circle. And it is well defined because, say, how many squares do we see? For each intersection point of green curves, we see a blue square. And say, consider this intersection point, B curve and C curve are intersecting there. And that is fine because B curve there, B circle and C circle will span a torus. So you can just map that square onto that torus. So in this way, one can define a map from surface into the Salvetti complex. And moreover, if you look at the blue vertex corresponding to the region up and front, one will see incoming F edge, outgoing A edge, incoming B edge, outgoing C edge, incoming D edge, outgoing E edge, and so forth. So there are 6 edges intersecting or incident on that vertex. And then, well, I'll just skip technicalities, but the link will be a circle and combinatorially a hexagon for the cubical structure. And the link of the Salvetti complex can be obtained by just taking intersection of small sphere around the vertex. So there are red vertices and blue vertices corresponding to outgoing portions and incoming portions of each circle. And therefore, the link of Salvetti complex will have 12 vertices corresponding to outgoing portion of the circle, incoming portion of the circle, and so forth. And A plus minuses are joined with B plus minuses. B plus minuses are joined with C plus minuses. That's because if you look at the torus, say, consider the torus spanned by A curve and B curve. Say A is joined this way, B is going this way. Then there are 4 types of corners, 4 types of edges in the link. One edge in the link is generated by incoming portion of B, outgoing portion of A, or outgoing portion of B, outgoing portion of A, and so forth. So A plus minuses are joined with B plus minuses. So this is the link picture. And if you just analyze the map, how does the link act? And the link turns out to be a full subgraph in the target. So it is localized symmetry, therefore it is pi-injective. So it is, again, this proof is also folklore, but clearly written by Crisp and Witt some years ago. But this fact itself, writing darting groups on 6-cycle contained surface group, has been known for almost 2 decades, proved first by cardiomes. So we call this kind of as label reading map because it is defined by transversely oriented and labeled curves, structure on surface. So cardiomes first proved that writing darting group on cycle of length L is 5 contains a hyperbolic surface group. His proof was completely different, but the results are the same. And for about 2 decades, this ACN for NLS 5 was the only family of examples writing darting groups contain hyperbolic surface groups. So naturally, people asked, does writing darting group contain hyperbolic surface groups? If and only if it contains 4 long cycles. So graph theorists call this as hole in this cycle of length L is 5. So is it if and only if condition? Or writing darting group, can you ask the same question and what's the answer? And the answer turned out to be false. So actually, there is a triangular prism graph. Consider complement graph of cycle of length 6. And consider writing darting group on that graph. So that this triangular prism graph In other words, it is a triangular prism graph. This is complement of cycle of length 6. And it turns out that it contains a surface group, hyperbolic surface group. And moreover, writing a Cox group, the answers are different. The answers are different. And well, actually one can use, so let me skip some facts and let me just describe a result. The result is using some graph. So it is very interesting because we employ some serious graph theory, like decomposition theorem for triangle free groups or square free groups. But the result is if the graph does not contain any long cycle of length at least 5, and if it is either square free, no induced squares, or triangle free, then writing the Artin group on those graphs will never contain any hyperbolic surface groups. And the proof is really something like a graph theory on surfaces. We analyze maps from surface groups into writing the Artin groups by the previous way. We consider transversely oriented labeled curves on surfaces and just analyze configuration of those curves. So it may well be called as graph theory on surfaces and prove some contradictions or conclusions. So finally, let me just mention questions. Writing the Artin groups, when does it contain hyperbolic surface groups? And the general answer is wide open, and even there is not a conjecture governing them. And number 2, I'd like to just focus on number 2. Does there exist hyperbolic three-manifold group which does never virtually embed into any right-angled Artin group? This is a very critical question. So can you find the hyperbolic three-manifold group which will never embed into any right-angled Artin group? If yes, then Love conjecture is false, because in the previous slides we have seen that if three-manifold group is LERF, then everything is true. Virtually fibers and virtually embedded right-angled Artin groups. So if one can construct hyperbolic three-manifold group which does never embed into any right-angled Artin group, then it will be very surprising. Love conjecture is false. If no, that will be excellent. If any hyperbolic three-manifold group virtually embedded into some right-angled Artin group, then they are all virtually fibered. So it is very concrete description for hyperbolic three-manifold groups. And writing the Cox groups, or one can generalize it as just consider even more general class of groups. So I'll stop here and thank you for listening.